Yes. Yeah.
Oh, okay. So the charged particle of mass 18 times 10 to minus 26 kilogram had charge magnitude of minus 6.4 times 10 to minus 19 coulomb and is accelerated by the potential difference before entering a region of the uniform magnetic field of a magnetic magnitude of B1 with, with the magnitude of 1.2 Tesla. It followed the path shown in the drawing and entered second region B2. So the first one determined direction of a magnetic field B1, determine the direction of number B is to determine the direction of magnetic field B2, and C is going to find out the velocity of the particle in the uniform magnetic field B1. And D, calculate the magnitude of potential difference used to accelerate charged particle prior to it following this path. So we have to apply right-hand rule to figure out the direction of the magnetic field. There's the magnetic force is resulting force out of the two vectors, velocity of charged particle V plus product of magnetic field B. So let me what? Hold on a second. So I think I should be okay. Hold on. Okay, maybe I just turn on this one instead. Hold on a second. And maybe just let me open up myself. Okay, so let me see my screen, right?
Yeah.
Okay, so now the charged particle moving along this travel path, which is S shape. Their path is just changed by magnetic field. Let me change color. When this charged particle enter the first uniform magnetic field area that has the curve to the second pass, straight pass with the radius distance 28 centimeter, right? And that is magnetic field. We don't know which direction of the magnetic field region 1 is pointing. And the same thing, you have second magnetic field, uniform magnetic field region number 2, that because of magnetic field, these charged particles have the curved trajectory along the straight line. So number 1, we have to find out direction of the magnetic field. So according to the right-hand rule, now this is charge, positive charge or negative charge. Is I believe this minus, how much is minus 6 point something, right? 6.4 times 10 to minus 19 coulomb, right? So there's negative charge. So if you apply the right-hand rule, so hopefully you remember the right-hand rule. That's like, you know, if you use this right hand, so this F is a thumb, direction of thumb. The V, index finger, is the last in the direction of velocity vector, and the B is third finger is the direction of a magnetic field, right? So now, if you use the right hand rule, the first direction of V is the pass 1, the first pass, straight pass. The direction of velocity V is left to right, right? And now, because these charged particles have the curved motion along the half circle. So that means the force pointing downwards. So they're dragging the charged particle downwards from the magnetic field. So if you apply that right-hand rule first, we gotta just apply this index finger to the what's that? The to the left, right? To the left. The left to the right, this index finger. And this force should be downward. So it should be like this, right? So, but here, so this is for the thing. Let's I don't know if you actually look at my right hand, but the thumb is pointing downwards, and the index finger pointing the left. I mean the left to the right, right? And the third finger pointing outwards, right? Are you with me? So
Is the thumb is the force?
yes,
Your
thumb is forced downwards, right? Because
Yeah.
that because you just bring that the charge downwards, so the force should be directing the downward, right? So the thumb is downward, and the index finger to left to right, and then the third finger pointing outwards, out of the page, right? But understand, right? But here, one thing you have to take into account, this is negative charge. Negative charge, so you have to apply the negative charge the direction of this magnetic field. So B field should be inward because the negative charge. If the positive charge, then this magnetic field should be outer page. But that's the negative charge, so you have to minus sign apply to this force. I mean the magnetic field, so that should be inward. Now, let me just draw the picture. So let's see. That might have a horrible actually drawing. So this is the index finger, and this is thumb, and this if just inward. So the index finger is actually Q V, that it's itself include the direction of the velocity V. So that is same as minus Q V, and this thumb pointing the force of downward. So that lead to this third finger inward of into the page. Okay. So if I write it this one as F B equals minus Q V cross product B. So here B1, right? So if you label direction of each vectors, then this FV is downward, and Q minus QV is the left, and the B1 is inward. That is like this, minus QV, the B1, and the downward as FB. Okay. And number B, same, likewise, number B could be easily actually, answer. So number B, you can use that the same. So now the path along the magnetic field region, B, is the direction of the velocity vector is right to the left, but the force direction is downward still, so that make the charge have the curve circular, moved along the circular path. So if you use that same analysis, same right hand rule to this charged particle on the circular path is, so let me just draw the picture too, so that thumb is pointing downwards and index finger pointing the left to the right because no negative charge applied. And because of that, third finger pointing out of page. So this is downward, FB. And this one is QV, which is minus QV. And that because of that, this magnetic field B2 should be pointing out of page. Same rule. So it's just like a number A. So
Wait, how do you know where the velocity is pointing? Because as you enter the field and you exit the field, like the velocity is in different directions. So how do you know which direction to point?
well, that's the travel along this red line, right? So it should be when this charged particle enter the region B, it should be right to the left. So it should be this direction.
Right to left. Yeah. So in the drawing though, you're pointing to the right, like left to right. So
No, right. No, which one? That the B1 or B2? Which region are you talking about?
B2, like
B2
the
is right to left, right to left. The charged particle along travel along this red line, like this.
Oh, is the drawing accounting? Oh, the drawing is accounting for it being a negative particle. So you
Yes.
switch. Okay, that makes sense. Yeah.
So the velocity pointing the left to right, but this is negative charge, so that negative Q times velocity vector V is pointing the left to right. Okay, so that's why you need to apply the right hand rule with this configuration. Okay, so with that idea, you can actually find the direction of force with the same vectorial, cross product of vectors. So FB is same like QV. I'm sorry, that's QV cross product time B2. Same thing. Like just like question A, this is downward, and this is the right, and this B2 because of that should be out of page. Okay, same thing. So here, they all just they all downwards. When the charged particle enters this uniform magnetic field area, this force must be pointing downward at entrance of the field regime, right? Doesn't make sense, right? So that's A and B. Before moving to the C and D, do you have any question?
No.
Okay, just pretty straightforward, right? So number C. The C, we have to find out the radius or velocity of this charged particle when it's entered B1, uniform field, magnetic field area. So hopefully you remember this formula. When the charged particle get into the uniform magnetic field perpendicular to the direction of the field, the radius that charged particle normally has circular motion along the curved path. So that radius of the circular motion is m, mass of the charge, times velocity v over q, the charge of the particle divided by magnetic field B. I already just gave you how this formula should drive the last session. So if you rearrange this equation in terms of the velocity v, then velocity v is r times q times magnetic field B over mass m. Well, all the numbers already given in this problem. So radius r here, diameter of this one is 28 centimeter. So radius r is half of that. So 28 centimeter divided by 2 is 14 centimeter, right? So that should be 0.14 meter. Because when charged particle enter this uniform field area that has complete half circle, so radius of this circle must be half of the distance between the straight lines. Right, so the R is 0.14 meter, and Q, absolute value of charge, is 6.4 times 10 to the minus 19 Coulomb. The mass of the charge is 18 times 10 to the minus 26 kilogram. And the B1 is already given, which is 1.2 Tesla. If you plug them all into this formula, then the velocity is 1.14 meter times 6.4 times 10 to the minus 19 Coulomb, 1.2 Tesla, by the mass of the charge, 18 times 10 to the minus 26 kilogram. Then velocity of this particle into that the B1 is about 6 times 10 to the 5 meter per second, 5.973 times 10 to the 5. Hold on a second. Let me move this one out of it. Yeah, meter per second. Okay. So now this is just pretty true. If you know that this formula from the basic ideas of how charged particle have the circular motion, then that is just all you need is to plug the numbers into this equation, and that's it. So that's number C. Do you have any question? No?
No.
Okay, then number D. So originally, in order for the charged particle injected into the constant uniform magnetic field, the charged particle itself should have some amount of potential energy. So that amount of energy fully converted into the kinetic energy along the path of the charged particle. So from that relationship, you can actually find the potential difference, from the energy conservation. So let me next one. Okay. Let me delete up some of this. Okay, so total kinetic energy. So basically 1 over 2 m mass times velocity squared, which is same as the um, potential energy of the charged particle. So that is additional energy is given by this formula. So now you want to find out, actually this should be E times delta V. So delta V potential difference is 1 over 2 m E V squared divided by charge of the electron. So if you do that, then the total kinetic energy is 1 over 2 times 18 times 10 to the minus 26 kilogram times velocity already given in number C, right? From number C, you can plug that into this equation. So that is 5 times 5.937 times 10 to the 5 meter per second. Then you have to divide it by charge of the electron. So that is the 1.6 times 10 to the minus 19 Coulomb. So you plug all the numbers into this simple formula, then potential difference of this charge injected into this uniform field area is about 2.0068 times 10 to the 5 volt, which is 200, about 200 kilovolt. So when charged particle with that amount 6.4 times 10 to the minus 16, 19, 10 to minus 19 coulomb injected into this area, two uniform magnetic field regions, then this particle originally should be charged with a 20 kilo electron volt. Okay.
I think like the original way that I tried to solve this problem was that I thought that in the beginning,
Mm-hmm.
because in the original problem it says that I thought that because it's like traveling through the magnetic field, there's like
Mm-hmm.
kinetic energy, but then it stops at the end and it has potential energy. So
Mm-hmm.
I said like kinetic plus potential energy is equal to zero, and then I try to solve for V that way. But in this case, since it doesn't stop at all, I guess, do you just
Mm-hmm.
only use the kinetic energy formula for change in potential?
Well, you and but basically you when this particle entered into the uniform field area B1, that comes with this amount of the velocity, right? So in order to create that amount of velocity into the uniform field, some amount of energy, the particle, charged particle must be charged with some amount of energy that is 200 kb. So that you just create some kind of like connection. It's actually, this one is more like, unit conversion rather than actually, energy conservation, because the 1/2 mv squared itself is just can be expressed with the electron volt. So when it comes into this uniform field, that amount of energy must be existing in the charge, and that produce this kind of like curved shape. So that injected energy, when charged particle actually entered into this uniform field, that depending on the initial potential energy or initial potential difference, the charged particle have a different amount of the radius of curved motion. So in order to create the 20 centimeter or 14 centimeter radius of the circle, that charged particle must be initially, charged with some amount of potential difference. And that kinetic energy is just only energy existing in the first charge. I mean, the first part of that injection of charged particle. So let me quickly simplify the description. Now you have charged particle injected into straight line, right? So that's travel into this uniform area. So now you know that how much the radius is created by the magnetic field, right? So that amount of just variation of circular motion is directly depend on the initial energy of charged particle. So when this charged particle comes into this uniform field, then that just radius is just you know determined by that initial charge. I mean initial potential energy. So when the charged particle comes with some amount of energy, then depending on the energy comes with the charged particle, that particle have various, different the path of the circular motion or orbit of circular path. So now you know that how much this charge, how much radius the charge actually has on the circular path. Then you can just you know retrace that the initial energy out of the particle from the amount of the radius which is created by the discharged particle.
But the radius differs in the different paths, right? There's 28 centimeters in the beginning, and
Mhm.
as it enters the second magnetic field, the radius
The
changes.
second magnetic field area nothing to do with this first, this problem. This has nothing to do with this problem because the only energy, the first energy only is given by the magnetic field of the first regime because that's what you know. So that what I'm saying is that the now in this problem you only know the radius of first circle, right? Half of circle. That the amount of the size of the circle only function of initial energy of charged particle. So if you charge particle has higher energy, then the particle should have bigger size of the circle. If you less energy, then this charge should have the smaller radius. So there's a one-on-one direct relationship between initial energy of charge and the radius of the particle travel along.
Yeah, so when it says calculate the magnitude of the potential difference used to accelerate the particle prior to following its path,
Mhm.
it means wait, calculate the magnitude of potential difference used to accelerate. So it means I'm kind of confused. Why do you not consider the second magnetic field? Because don't you, because it's following it goes through both of them, so the kinetic energy would change going through both of them because they're different velocities at both of them.
Because second magnetic field doesn't affect the initial energy. How that can actually be, the main reason we can actually find out the number of initial energy because we know the radius of first pass in the uniform B field area.
But I thought that potential change, like difference, is final potential minus initial potential, right? So you would have to know like the final potential after it goes both of the two magnetic
Mm,
minus the
I
initial.
believe this question asks that the initial, how much that initially the charge actually um, the, initially charged in their potential.
It says like calculate the magnitude of the potential difference used to accelerate the charged particle prior to
Yes,
falling.
yes, that's what it's saying. The prior to the actually following the path.
So if the wording was changed to say after, would you need to know both of the
Well,
radiuses?
yes, after if you want to find the potential difference between initial state and the final state,
Yeah.
obviously while the charged particle travel along this S-shaped path, this charged particle will lose the energy. Then that statement totally different from the initial energy statement because
Okay.
it keep losing the potential energy while this charged particle go along this travel path. But this, I believe, this question is asking originally how much that charge actually this particle originally charged in potential energy or potential the voltage actually. So
So if it says
it
so
just
if
simply
it's
speaking, it's asking how much energy does initially this particle actually has.
yeah, so if it says initially like how much energy does it have? So you
Mm.
use the electric or magnetic field of the one that it's entering first. Is-
Mhm.
Okay, that makes sense.
Yes, yes. So that one of, as I just said, the one-on-one relationship. So like its kinetic energy is just determine the size of the circle. So if you know the size of circle, you can neutral back like the initial energy because that energy. is converted to the amount of the radius, or actually just the size of the radius also depend on some other variables too. But now this question only asks the initial energy. So all you need is just convert that the energy from maybe joule to the volt or electron volt. That's why I just told you that this is more like a unit conversion rather than actually energy conservation, because there's not, no actually potential energy involved in the way to solve this problem. Now, the initial kinetic energy. Now you want to express it into that same kinetic energy in the electron volt unit out of configuration of the circular path.
Yeah.
So there's no other part of this dynamics involved in the way to solve this problem, because B2 region has no connection with the initial energy or initial velocity. If you want to know potential change after this travel pass, then you have to find out energy loss to the second pass of the magnetic field, and you have to know the size of the second radius too. Then you may be able to solve that the potential change energy change of the potential energy from beginning and end. But now this only asks how much energy is given in this particle before entered into the B field in the B1, the B field origin. Okay. Does it make sense?
Yeah.
Oh, okay. So that's the only one problem you asked me on your email, right?
Yeah.
Okay. Do you have any other scheduled for the quizzes or tests?
I'm taking my retake for the RC-DC circuit test
Mm-hmm.
tomorrow, and then Friday I have a magnetism test, and then Friday after school I'm taking a retake for this quiz. Yeah. So I have three tests this week.
Oh my gosh! Tomorrow is scheduled with three tests.
No, tomorrow is just one test, Friday is two tests. Yeah.
Oh, the tomorrow is one test. So the last of the week is scheduled with three tests
Yeah.
in physics. Like crazy. All right. I have some. Do you, so you haven't actually emailed me the next topic on your semester.
Oh, oh, I
So
yeah. I'll do a reminder and I'll ask her during class tomorrow. Yeah.
do you think there's a lot more topics actually in the electromagnetism and actually magnetism too. We can go over that topic today. And once you figure out the schedule for the rest of the semester, you can email me and I'll prepare the next section with that topic. Sounds good?
I think also I was wondering if you could do a like quick review on the magnetism unit, just because I have my unit test this Friday and I'm not
Okay.
super confident on this unit. It's just like I think conceptually it's a little bit hard for me to understand. So
Okay. Whatever you want, and just you want me to go back to the review the magnetism one more time.
yeah, just like a quick like review. I think I
Okay.
understand like this really basic stuff, like I think
Mm-hmm.
right hand rule, like the F equation, force equation, radius equation, period equation. But after that, like I get a little bit confused.
Have you learned the Ampere's law
Oh
yet?
yeah, we learned that yesterday, but I didn't understand that either.
Okay. Well, because we didn't actually cover that topic yet, so do you want me to go over the chapter 29, the magnetic field due to the current, and maybe Ampere's law too?
But yeah, sure.
That's part of the next test too.
Yeah.
Okay, then I can go over that. So yeah, I know this is getting more and more and nasty. This is like a advanced topic even in the college, so it may not easy to easily digest all the content, but you know, but good things is that this is my actually major subject. I normally actually just work on. Hold on. So let me then I should probably reopen it. Uh, where is it? Okay. Okay, let me open that up again one more time. Okay. Um, so, it's I don't know how your school teacher actually taught this chapter, but I can quickly just run through that the topic, and you can maybe find some. Oops. Okay, hold on a second. Let me close it. I don't know why it's not working properly. Let me just close it up one more time. And, okay, let me open this up. Okay, so um, when the current flows in the wire or any kind of like a circuit, then that normally have intrinsic magnetic field produced. So if there's a wire and the current goes along this wire and some distance from the area of your interest should have the magnetic field. So that if you think of that at point P, then this is just a small segment of area. So ds actually segment of the current path, and this current I goes along this wire. Then if the distance r, and that's small amount of the current along this small segment could be current times the segment ds, and the B field from this small segment onto the point of the interest P be inward into the page, and that is the B magnetic field. This magnetic field dB from that small segment of the current be expressed with the mu naught over 4 pi and I ds and sine theta, if that is the angle between the IDS and the displacement vector of the this magnetic field at position P, then that is also that's like the formula you already actually learned from the chapter 28. So next step is you gotta actually just integrate this magnetic field to find out how much magnetic field is just produced by the total path of this current from beginning to end. So in order to find the genetic expression of the magnetic field out of the wire with the current I, should be dB equals mu naught is 4 pi I ds. Now is sine theta. ds sine theta could be expressed with the displacement vector r over r to the q. So that is